Hello.
We will wait for 5-6 minutes, after which we will start. Okay. Okay, good evening, everyone. So, my name is Abhishek Munshi. I am a PMRF research scholar at IIT Jodhpur. So, our lecture is about advanced power electronic and control. So, actually, today we will discuss a little bit more about the single phase rectifier with analytical analysis and three phase rectifier. Last day, I had give you a brief introduction to it and calculation. So, I will go more into deep about the single phase rectifier. So last day we had discussed about the R load, and we will discuss today with the different loads. So first, let us consider a single phase rectifier with half wave rectifier with L load. Okay. So if you have a L load, so first we'll discuss about the uncontrolled. So this is the structure for this is our input AC signal. This is the L load. This is my input, where input is Vn equal to Vm sine omega t. So what will happen in this case? So if we look into the graph, so this is my Vn, fine. So this is my Vm, this is my minus Vm. Now if we consider the output voltage, then what will happen? See, in the first half cycle, when diode conduct, this L will charge, right? L will charge. So we will have V0 equal to V in, that is equal to Vm sine omega t. So that means L di dt, that is equal to Vm sine omega t. So if we integrate di, we'll get integration 0 to omega t Vm by L sine omega t dt. Right? Is it clear? Any doubt? So the I for the first half cycle will be It, if we consider it's Vm by omega L 1 minus cos omega t. Now since inductor will store the charge, what will happen in the second half cycle? It will try to discharge it. So in the second half cycle, it will try to discharge to 0. Okay. So what happens in this case, the conduction angle of the diode became 2 pi. This is my pi, this is 2 pi. Okay. And what will be the voltage across the diode? Since in the two half cycle it will minus, so voltage across the diode will be 0. Fine. So the in conclusion you can say that the average current will be Vm by omega L, and the RMS voltage will similar to that of the R load, that is Vm by root. Okay. And what will be the extinction angle? Since the extents are 2 pi, so extinction angle that will also be 2 pi. Okay. And since the voltage across the diode is 0, because the circuit turn off time is 0, because the circuit will not turn off, it will run again and again. Okay. So that is what happened in case of a half wave rectifier with L load. Now what will be the case if we have RL load? So in this case, so we have a resistor and an inductor. This is R, this is L, this is my Vm sin omega t. Fine. So my input will be similar in this case also. So what will happen in this case for the positive half cycle? Suppose when at the positive half cycle, when diode will conduct, diode conducts, the output voltage will follow the input voltage. Why? Because in the positive half cycle, it will behave as a closed switch. So we'll get the output as similar to the input. Now, for R load, we know that for R load, last we had discussed that the conduction angle of the diode is pi. So I will not write conduction angle again. So I will write it in with the help of symbol. So conduction angle pi. And extinction angle is also pi. Now for L load, we found out that beta for L load is 2 pi. So what will be the beta for RL load? So it will be in between of pi to 2 pi, right? So what will happen? The inductor will store some energy, and it after the positive half cycle, it will try to discharge it. So it will store some energy in the negative half cycle also. So the output waveform will look like this. Okay, fine. So in this case, what will happen if we calculate from 0 to pi? So this is 0 to pi, and this is my beta extension angle. Okay. So from 0 to pi, my V0 is greater than 0, my I0 is greater than 0, since also my power will greater than 0. So my source is delivering power. Now from pi to beta, on that case, what will happen? My V0 is less than 0. My I0 will definitely greater than 0. My P0 will be less than 0. So in this case, what will happen? My load will delivering the power to the source, just like an inverter. Now for beta to pi, 2 pi, my V0 is less than 0, I0 is less than 0, and P0 is less than 0. So on that case, it will not deliver any power. Okay. So what will be the average voltage? So if we calculate it, it will be Vm by 2 pi 1 minus cos beta. Okay. and here also the conduction angle is equal to the extension angle. Okay, if you have any doubt you can ask. Yes. Okay, fine. So now the next case, now we have an RL load plus a freewheeling diode. Okay, in this case we have this diode. This is my input. We have an RL load and we have a freewheeling diode additional to it. Fine. So what will happen in this case then? So this is my input. See, in the first half cycle, it will conduct as similar to the uh, any other load. But here the inductor will store energy, but in the second half cycle, when our see in the first half cycle, the circuit will look like this. When on, and when the diode is off, it will look like, then this diode is in forward bias state, and whatever energy this inductor will store, it will discharge through this freewheeling diode. So in the negative half cycle, there will be no voltage found. Okay. So in this case, we have see that this is very similar to the R load, and so the calculations will be similar. But we have to understand the thing that in case of the RL load with the freewheeling diode, the inductor will discharge through the freewheeling diode during the off state. Okay. Now, next case, uh, let us consider a RE load. So here, what will happen? This will be my input. Consider V in. Let us consider that this is the value of E. Okay. So here what will happen, up to the E, if you see that the voltage difference will be zero, so it will not conduct. So after E, the diode will start conducting. And again, in the next half cycle, it will repeat. Okay. So this is 0 to pi to 2 pi. So if we consider it in this way, that we have 0 to pi total cycle, 0 to theta. This is my theta. Let us consider this as theta. Then this will be pi minus theta. So the next cycle will be theta to pi minus theta. And last cycle will be pi minus theta to pi. So this is the conduction period. So if you have to calculate in between of this. Okay. So here, if you calculate the I0 average from theta to pi minus theta during the conduction time, so it will be 1 by T0 to T I0 T dt. So it can be replaced by theta to pi minus theta, and this will be 2 pi, right? Total time period. So this is Vm sine omega t minus E by R d omega t. So if we calculate it, our I0 average will be out to be 1 by 2 pi R 2 Vm cos theta minus E pi minus 2 theta. So this will be my average current in case of a RE load. Now next case will be RLE load. Okay. So I'm discussing about the every load for the half wave rectifier. RLE load is nothing but if you consider a DC motor as a load, so this will similar to a DC motor, right? So here what will happen if you consider my input as this. So here also there will be a specific value of my E. Okay. So for the L load, what will happen? It start conducting after E, but it will conduct up to this, up to, and again it will start and conduct. Okay, so this will be my extension angle beta because L will store some charge for the some time period. Okay, so here the conduction angle increases due to the inductor. Here the conduction angle increases, obviously from the figure it is clear, due to the presence of the inductor. Okay, so we'll get more than theta to in between of beta. Okay, fine. It will conduct from theta to beta. So now we will discuss about the half wave with un sorry with control load. So if you have any doubt, you can say, and after which we will again start with the control load. What output you are asking about? I don't understand. You can unmute and ask me the question. So here see that it will conduct similar to the RE load, but due to the L load, it will store some energy and it will extend after certain angle. So just consider that is beta. So that's what I'm saying. Okay. Now let us consider with control rectifier, that is with the help of XCR. SCR with L load. Last day we had discussed about the R load. This is my output, this is my input. So this is my input. So in case of SCR, uh, last day I had discussed that SCR will trigger uh, after a certain angle. Like if you, so if you consider the gate current, if you see that after a certain angle, the gate current will conduct. Right. So what will be my output? After the gate current will close, then the output will start conducting whenever it will trigger, right? So this is an angle alpha, last as I said, that is triggering angle. Or in some book you will see that it will be called as firing angle. Why? That after which the SCR will turn on. Okay. So unless and until the SCR will turn on, it will not conduct the energy, right? So that's why the output will be like this. And for L load, it will store some energy up to a certain point, that is beta. So output will look like this. So if you consider the output current will be in between this. Fine. So what will happen in this case, that my input is Vm sin omega t, that is equal to V0. So L di dt will be Vm sin omega t. So I will be Vm by omega L cos alpha minus cos omega t. Last time it was 1 minus cos omega t, but here it is replaced by cos alpha. So what will be the extinction angle? 2 pi minus alpha. This is alpha. This is my 2 pi. So extinction angle will be 2 pi minus alpha, right? So if we replace it with beta, then the current equation I0 can also be written as Vm by omega L cos alpha minus cos beta. Okay, clear? Now with the RL load, what will be the scenario? I'm discussing because we'll solve some problems related to these loads. This is my RL load. Okay, so RL load, what will happen? Let's consider this is alpha, this is beta, and it's 2 pi. This is alpha 2. So here what will happen? It will store some energy similar to that of the L load. Okay. Fine. This is my V0. This is my V. This is beta. This is alpha. This is pi. So what will be my conduction time? That is beta minus alpha. And V0 average, if we calculate it, it will be Vm by 2 pi cos alpha minus cos beta, similar to the L load, as the curve is similar. And I0 average will be Vm by 2 pi r cos alpha minus cos beta. Okay. Now what will be the case if we have a RL load plus a freewheeling diode? So here what will be the case? The inductor will discharge across the diode, as I said. So there will be no stored charge energy. So alpha. So this is similar to the R load. Okay. This is V. This is VG. So here gamma T, that is equal to pi minus alpha. VG average will be similar to the R load, that was last day we had calculated Vm by pi 1 plus cos alpha. Okay. And the freewheeling diode will conduct from beta minus pi. Right. In case of the discontinuous, but we are considering the continuous conduction mode, so it will be in between pi to 2 pi plus alpha. That is here. Okay. So now what will happen if we consider RE load in case of control rectifier half wave? So in case of RE load, if you consider this as my E, so it will conduct from here. Okay. So in this case, if you calculate the V0 average, it will come 1 by 2 pi. Try to put down the formula because it will help you to solve the problem. Alpha plus pi plus theta Pm by omega cos theta plus cos alpha. Okay. The I0 RMS will be 1 by 2 pi r square. So this is a complex one. So if you can solve the integration, then that will be easier to understand. Don't try to remember the formulas. Okay. So the next case will be for RLE load. RLE. So this is my E. So this is E. This is suppose alpha. It's theta. What will happen? It will conduct up to suppose beta. Okay. Fine. So this is under single phase. Okay. Any doubt till this part? So now a case I'm considering, if you consider a full wave case, last day I had and discussed a little bit. So if you consider a full wave case, designing rectifier is very easy. And this is one of the most easiest part. So let us consider this as a load. Okay. So the load may be RLE type, may be RL type. If the load is like RL or RLE, this is my input. My output will be like this. Okay. So in this case, what will happen? The value of the conduction time will be pi minus alpha. Circuit turnout time will be pi minus alpha by omega. My V0 average will be 2 Vm by pi cos alpha. Okay. And the average current across the thyristor will be I0 pi by 2 pi. This is a simple process to calculate. If you see from here, the thyristor will conduct from alpha to pi plus alpha. So the total time period is 2 pi and is conducting for pi time. So it is pi plus alpha minus pi, that is pi. So that is the trick to remember the average is total conduction time by the total time. Okay. Now similarly, if we have a RE load, I'm not drawing it. So what will happen? There is an additional E over here, E factor. So the waveform will be like so. So here, if this is theta, then the target turnout time will be, this is theta, 2 pi theta. So V0 average will be 1 by pi Vm cos alpha plus cos theta plus E alpha plus theta. And I0 will be V0 average minus E by R. Simple. Okay. So that's for the single phase rectifier. So if you have any doubt, you can ask. I hope you don't have any doubt here. So remind it. And we'll start three phase. See, it looks like a little boring, but I'm discussing all the possibilities so that we are able to solve the problem properly. Okay. See, for the three-phase load, let us consider a half wave case first. It will connect with a load. Okay. So drawing the three phase is a little difficult. In freehand, actually you have to do some angle division like 30, 60, 90 in this way, and then just cut it out. Then that will be easier to understand. But it's freehand, it will be a little bad. Try to understand it. This is a 90, this is 120. So from 120 there will be another. So it will look like this. Okay. Fine. So what will happen that throughout the cycle, some conduction will happen in this, the T3. If this is T3, this is T1, this is T2. T3 will conduct, and during this cycle, my T2 will, sorry, T1 will conduct, right? So first one will conduct. Since first one is positive, so if you see the positive, which one is positive over here in the, up to this part, then that will conduct. This is T2 will conduct like this. So this is the trick to remember. So that is how it will conduct. So in case of R load, for RL it will conduct up to a certain time, right? So it will look like this. This is T1, this is T2, this is T3. Actually I have to use three different color, I didn't use it. Okay. For RL load, it will conduct a period of time, and then suppose this is next one. and after which the next one will conduct. Okay, so this is my T3, T1, T2. This is for RL, for R load. This is for R load with diode, not for thyristor. This is for thyristor. Okay, clear? So try to remember the formula. In this case, the VGD average will be, and it can be written as 3 VML, that is maximum line voltage by 2 pi cos alpha. So maximum line voltage will be root 3 of the voltage. This is the relation. Okay. Then what will be the average? You can also write it, since VBL can be written as root 2 of the total line voltage. So it can also written as 3 root 2 by 2 pi VL cos alpha. Okay. So the V0 average we calculate for greater than 30 degree in case of R load for thyristor based, and it will be 2 pi by 3 integration 30 plus alpha to 180 degree Vm sin omega t dt. So if you integrate it, the average will be root 6 by 2 pi VL 1 plus cos 30 plus alpha. Or you can replace it with root 3 2 pi. You can replace it with VML also. Okay. VML is I root 2 pi. Okay. Now similar case will happen for the full wave rectifier, where the circuit will look like this. So what will happen? This. So in this case, actually the V0 by Vm per unit will be 1.5 per unit. Okay. So if we calculate the V0 average, I'm not drawing the diagram. You can find it in any book or in the lectures. So VML by pi cos alpha 3 root 2 by pi VL cos alpha. Now here that will be 30 will be alpha greater than 60 degree. On that case, that will be average will be for the thyristor 3 VML by pi 1 plus cos 60 plus alpha. So we have to solve some problem related to it, otherwise it will not. So the first question were in semi converters, it will be single quadrant, double quadrant, three quadrant, or none of the mentioned. Try to answer it. See, for which we have to discuss a little bit about the semi-converter. What happens in semi-converter? So if this is a full in semi-converter, we have suppose two thyristor here and two diode here. Now your supply is connected in this way. So on that case, what will happen? If this is my input, my output will conduct from alpha to pi. Okay. But there will be another case. This is a symmetrical configuration. It may be asymmetrical configuration like this. So whatever be the configuration, the output voltage will be. So what will be the converter quadrant of conduction? Now you can able to understand and answer it. Okay. Try to answer. I am given 2 minutes if you will to answer. Okay. Answer with single quadrant because from the figure it is easier to understand that the voltage and current can conduct only in the positive due to the diode. This is single. Next question, there is a full three-phase full control thyristor. You have to consider the RMS current. You have to calculate it with the help of the formula which I had. So this is my DC link voltage. This 420 volt. This is given here. So the formula will be 1 by 2 pi 0 to 5 d square d omega t. If you integrate it, you will get ultimately this is the formula. You can remember this formula. This is ID by root 3. So if you are able to have to calculate the ID, so that will be PD by VT, the total power. Power is given as 50 kilowatt by VD is given as 420. So if you put it, it will be 119.05. So 119.05 by root 3. So this is the answer. Okay. Next question. This is also a three phase. Calculate the percentage reduction. Try to answer it. Fine. So the voltage reduction, if you see, it will be 6 if LS IDC. You have to calculate the IDC. It will be 27. So it will be reduced by 3.85 percentage. Okay. So next question for a single phase dual converter. So we have a converter with C1 and C2 connected in parallel. Which relation among the following is true? Try to answer it. So for your understanding, I'm saying that the dual converter has two bridges. Okay. So if you have a bridge and if you have another bridge in invert way. So this is a dual converter. You have the load in between of this. Okay, and the supply is connected. So you are asked that what will be the firing angle if C1, if this is C1, this is C2, the firing angle of this is alpha 1, this is alpha 2. What will be the relation between this? Okay. Say it will be alpha plus alpha 2 equal to 180 degrees since both are full wave. So I said that this is Vm by cos alpha 1, this is Vm by cos alpha 2. So in this case, the cos alpha 1 must be equal to cos alpha 2. Cos alpha 1 will be, since it is inverse, so it will be 180 degree minus alpha 2. So alpha 1 plus alpha 2 equal to 180 degree. Fine. So next question is a single phase full bridge full control thyristor rectifier that is feeding at 30 volt 50 hertz sinusoidal source from which is feeding it into the rectifier. The commutation overlap angle you have to calculate. Fine. So the commutation overlap it will happen when there is an input side inductor. Generally, if you use an input side inductor, then only it will arise. Okay. So that was an effect of the source inductor. So if you have, this is my power source, if you have an inductor after which you have suppose a freewheeling diode and your load, for example. So on that case we will get the commutation angle. Okay. So commutation angle for of one pulse for a half wave, the relation is delta V0 is F LS I naught. So commutation angle that will be denoted by mu. Okay. So my V0 average will be alpha plus mu Vm by 2 pi. For two pulse, that is for full wave, this delta V0 is equal to 2 omega Ls by pi I naught, that is 4f Ls I naught. Ls is the input side, source side inductance. For 6 pulse, that is for 3 phase, which will be I naught is sorry, Vml by 2 omega Ls cos alpha minus cos alpha plus mu. Mu is the commutation angle. For 2 pulse, and then write the I naught, that is Vm by 2 omega Ls cos alpha minus cos alpha plus mu. Okay, so just use these formulas and you can able to solve it. So if you use the formula, you can able to solve it. Just put the formula Vm by pi cos alpha plus mu, that is equal to 4f LH I naught. Since it is a single phase, so it will be two pulse. You have to use the formula. And able to solve, the value is 4.80 mu values. Okay. So next question. So which are the two most dominant frequency of the source current? You have to calculate it. So the two most dominant frequency, if you have to calculate, it will be for n equal to 1, 3, 5. We know that for the odd harmonics of Fourier. So that will be AF, third harmonic. So first harmonic and third harmonic will be the answer. So this is a 50 hertz. So 50 hertz and 150 hertz is the correct answer. Okay. The next question: the fully controlled three-phase bridge rectifier is working from 415 volt, supplying a constant current. So let's assume that a large inductive smoothing and neglect overlap. Okay, and find the RMS current. So similar to the a problem which I had solved previously. So try to put that formula and calculate to solve. So try to remember this, that in case of the three phase, the RMS current will be the fundamental current root over of 2 by 3. Okay. So if you put it, that's 100 is given. So it is 100 root over of 2 by 3. And so it will be 81.65. Okay. So the next, as the average voltage of a three phase bridge rectifier is given, find the maximum value of the line voltage. Vm is given, you have to calculate the VL max. Okay. So as I mentioned there that the output voltage is 3 Vm by pi in case of a three-phase rectifier. So VML you have asked to calculate, so that is 0 by 300 volt, right? Since it is 3 VML by pi, so it will be inverse of it. Okay. Now next question, which of the following is the correct statement? We have to answer it. One is multi-pulse converter do not produce harmonics. Multi-pulse converter produce harmonic at specific order. A number of harmonics produced increases with the pulses. Pulses in the sense that is the phase. Okay, so try to answer it. So the multi-pulse converter will produce harmonic at specific order, which can be minimized. For example, in case of a converter, we generally try to remove the third harmonic and the fifth harmonic, the odd harmonic components that will produce unnecessary noise into your converter. Okay. And the last question, in a three-phase semi-converter, the firing angle is 60 degree. C-phase semi-converter, that is, it may be symmetrical, asymmetrical, like this. The diodes are connected like this. So in this case, you are asked to calculate the freewheeling diode, how much time it will conduct. So if you have a freewheeling diode here in the load, okay. So this is the last question. Try to answer it. So in case of semi-converter, obviously the alpha will be less than 60 degree, but the freewheeling diode does not comes into play because since throughout the cycle, as I said, it will conduct, so freewheel diode will not have a chance for the inductor to discharge. So it is zero. Zero is the correct answer. So that's all for the day. So if you have any doubt, you can ask. Otherwise, you can leave. Okay. Okay. Thank you. Okay. That's all for the day. So
Thank you, sir.
Okay, thank you.